Hi, this is my submission for the 3D and shader programming assignment. For my first shader, I made an ocean. My personal goal for this shader was to not use any external textures. Thus, the material is completely procedural. As we'll see, this came with both advantages and drawbacks. Firstly, let's look at the waves. They were created using the material function WaveMaker. As we can see, this is a huge mess. A better implementation would be written in HLSL, where a for loop could be used that also randomizes the values for the sine waves. As for how the function works, it just combines a variety of sine waves with different rotations, frequencies, movement speeds, and amplitudes to create the illusion of a simulated surface. Secondly, let's look at the foam. It uses a distance field fed into an animated sine wave to produce a dynamic effect that responds to its environment. And that looks like this in code. Quite a simple implementation, but it does the job for my purposes. Finally, let's look at the droplets. These are produced by feeding an animated Voronoi texture into an animated sine wave. The results sort of look like droplets. This could be hooked up to some kind of weather system as well. And now let's go over a little bit of the shader code. The production of the colors is simple. We simply use the depth fade function to create a named reroute node called water depth, and then we use this to color our water. This depth is also used for the opacity, which varies with the depth. Because I want both a height map and a normal map for the waves, I needed some way to compute the normals, and I didn't want to use the built-in height to normal function because I assume it uses some kind of looping over everything. So instead, because I used sine waves, I could easily calculate the derivative of my function and simply output that. However, as we can see, the shader is still very poorly optimized. If we press Alt-8 to turn on the shader complexity mode, we can see that our ocean is completely white, which is the far right of this spectrum, which means it's extremely hard to compute. One means of optimization could be that instead of actually calculating the sine waves, we simply feed it something like a 1 by 512 texture of a slice of a sine wave, and simply rotate that, scale it, and move it, and that should be quite a lot cheaper. Additionally, we're using refraction and transparency, which are both known to be quite expensive to compute. For our next shader, let us jump into play mode. If I press the left mouse button, it seems that I came a little too close to this giant delicious looking mushroom right here. But worry not, this effect subsides over time, leaving no permanent damage and possibly making us a little bit wiser in the process. There are a couple of parts to this shader. Firstly, we have the distorted UVs, wherein I use an animated Perlin noise mapped to world position to offset the screen space UVs. Secondly, we have the two kinds of hue shift. Firstly, we have this one, which is dependent on the normals of the objects, and provides a kind of rolling effect where the hue change wraps around the objects. The other is a simple hue shift for the entire screen. As a final touch, I saturate the entire screen. For our last shader, let us immediately jump into play mode. As we can see, someone forgot to turn on the lights, but fear not, we possess the superhuman skill of echolocation. I apologize for the lack of sound here, but as a reconciliation, the footsteps make a sound. And it also creates a visible sound pulse. There are a couple of things to note before we take a look at the shader. Firstly, the fading. The speed at which the signal fades is affected by proximity to the source of the sound, the velocity of the player, and by a set fall-off over time. And this is handled on the end of the blueprint. So if I stand still, it takes a long time. If I move, it fades very quickly. If I move and then stop, it fades a little bit faster than when I'm standing right there, but still quite slowly. The shader's blend mode is additive, meaning it adds in value to whatever already existed before it. This is the key to having multiple signals at once. In Begin Play, I add however many of the exact same post-processing material as needed to the camera. In this case, the maximum allowed amount of signals at any given time is 16. If the player attempts to supersede this limit, it simply won't send out the signal. Now, let's have a look at the shader. The first step of the process resides here, where a kind of depth is calculated, but instead of it being to the player, it is to a defined origin. In this same comment, we also see our shading model, which is similar to Gooch shading, where the dot product is remapped from -1 to 1 to 0 to 1 to preserve the detail in the shadows. This is not true Gooch shading though. Real Gooch shading maps black to a cool color and white to a warm color. Secondly, this distance is used to calculate a physically accurate falloff depending on the distance. The output of this is watts per meter squared. Above it, we combine this falloff with our Gooch shading. Next, we clamp the value softly using this function. As we can see, this is different from a regular clamping function because it preserves some amount of detail for values that used to be above 1, but we still clamp our values between 0 and 1. Aside from this, there are a couple of aesthetic extras. Firstly, we calculate a pulse that grows and at its most intense at the very edge. This prevents new pulses from just appearing out of nowhere. Secondly, I added a subtle sine wave effect from the origin, which is happily only noticeable for the footsteps, but I like how it creates a nice looking interference pattern sometimes. And lastly, we do the compositing, where we add this onto our post-processing input 0 instead of just setting. As for the optimization of the echolocation shader, we have a couple of clues as to the performance, but it is hard to know the full truth. And one hint is the amount of instructions. And here we have 124 and 131. If we compare that to our water shader, it has 2,725 base pass shader instructions. And this should hint at our echolocation shader being cheaper, much cheaper to compute, but we can't know completely for sure. We have some expensive operations, like divisions are quite expensive. We have a built-in distance function which has an expensive square root. We have sine, which is also somewhat expensive, but from what little we can see right here, this should be cheaper than the water shader at least.